Welcome to me and Kevin's assignment on time travel. Now, time travel, actually just time dilation, explained by the two of us, me and Kevin, who gave up on hoping that our teammates would help. As you can tell, our two teammates did not help at all. So what is time dilation? Now, in the beginning, which is the one slide that Bradley almost helped on, he said time travel, which time dilation is not exactly time travel. It's the speed of light being constant, creating points of reference to it's points of reference. Okay, so again, this was not my topic. I was not. So the dictionary definition for it is a slowing of time in accordance with the theory of relativity that occurs in a system in motion relative to an outside observer, and that becomes apparent especially as the speed of system approaches that of light, also called time dilation. So that means that to different observers, time passes differently when you're going different speeds. So, for example, we're going to look at the example and then look at the formula and then solve the example. So, Steve flies past the Earth at a speed of 0.0800 times the speed of light. Of course, he can't reach the speed of light because that's not possible, and this is more accurate. So, his cousin Jim stays on Earth. At the same time Steve passes Earth, they both turn on a stopwatch. After 60 seconds have passed, Steve stops his watch. What time would Jim's watch be? So, the formula for this would be, let me just whiteboard it. Observer time. Okay, I need a new marker.
The best example of time dilation are from the atomic clocks in satellites. A satellite moves at about 8,700 miles per hour around the Earth. That means that every day the atomic clock in a satellite is offset by about 7,200 nanoseconds compared to a clock on the Earth.
For time dilation, which is your observer time equals the proper time, so the time that it actually is, over, or the time that it actually is, in our scenario, we have this little Earth, the time that it actually is would be, we're taking the reference of him over the Earth. So he's the observer, Jim's the observer, Steve is the person taking the action. So he's the observer, he's the proper time. So you have proper time over the square root of 1 minus velocity over speed of light squared. Now, you can simplify this down to this triangle T to observer time equals triangle TO, proper time, over 1 minus V for velocity, C for speed of light. Speed of light, okay, so now we take into account what our problem said. Okay, so it's 0.800, the speed of light, 60 seconds. So, we have observer time equals 60 seconds over square root of 1 minus 0.800 speed of light over speed of light squared. Now, simplify it down to 60 seconds over 1 minus 0.640, which can be simplified down to 60 over 0.600. Now, you get your observer time to be 100 seconds. So, when 60 seconds passes for Steve, 100 seconds passes for Jim. That's insane. That's an insane amount of time. This is why it needs to be factored in. Like Kevin said, if I can connect his video with mine, there needs to be this application. This needs to be factored in when they're setting the atomic clocks in satellites. So, this has been my presentation. I hope I get a good grade on this. I'm sorry this has come in so late. I was relying on a teammate who just completely was supposed to take control and did not. I'm sorry about that. I should have taken initiative, should have not trusted Bradley, but I hope this is good because I used Sharpies on a perfectly good plastic table, and my parents are probably going to be not too happy. Bye, Miss Wallace.